Effect of geopolymer on the unconfined. Compressive strength value of clay soil. Abstract weak soils are encountered in many regions, which lack adequate stiffness and strength to resist the loading due to construction project. Soil improvement is a technique for amendment of these geomaterials. Two common method of soil improvement of soil mechanical and chemical stabilization. Commonly mechanical procedures include the compaction and earth reinforcement. In the recent years, treatment with geopolymer as a chemical stabilization technique has been widely investigated to earth improvement. Many experimental studies were conducted on the behavior of soil stabilized with the geopolymer. Their results indicate that employing geopolymer improved the resistant behaviors of stabilized soils. Keyword: geopolymer, fly ash, stabilization. 1. Introduction. In cement-stabilized soils, the stabilization mechanisms are associated with hydration and pozzolanic reactions. When lime is mixed with clayey soils, the clay particles become closer and the soil is stabilized through flocculation and pozzolanic reactions. A major issue with conventional soil stabilizers, i.e., OPC and lime, is that their production processes are energy-intensive and emit a large quantity of CO2. For instance, approximately 1 ton of CO2 is emitted for the production of 1 ton of cement. Furthermore, the raw materials readily available for cement production are being overconsumed. Therefore, civil engineering industry is always searching for new, viable sustainable alternatives to replace Portland cement as soil stabilizers. 2. Review of literature. Cristello et al., 2013, studied the role of calcium content in alkaline activation of fly ash used to stabilize soft soil. Alkaline activation of fly ash is also known as geopolymerization. The soil used in this study was marl, contains high calcium carbonate content. Soil consists of plastic limit 19.7%, liquid limit 51.9%, OMC 18%, MDD 20.8 knots per cubic meter and UCS 60 to 100 kPa. Two types of fly ash: Class C fly ash, high calcium content, and Class F, low calcium content, were used, which obtained from pulp and paper company and a thermoelectric plant respectively. Soils mixed with lime and with cement were also tested separately. For activation of fly ash, sodium-based alkaline activator was used, which was a mixture of sodium silicate solution to sodium hydroxide solution. The ratio of sodium silicate to sodium hydroxide by mass was 2:1, while activators to fly ash ratio were 2:1 and 4:1. UCS samples were prepared and test performed after 1, 4, and 12 weeks of curing. He et al., 2013, investigated mechanical properties and microstructure of soil stabilized by geopolymer. For the precursor to industrial waste, red mud, RM, and rice husk ash, RHA, at varying percentage were used. RM is the major waste produced by the alumina refining industry, while RHA is produced by burning of rice husk. Geopolymerization reaction was initiated by dry mixing of RHA and RM with sodium hydroxide solution. This study was carried out into 4 sets of test samples. In test samples A, the solution to solid ratio weight ratio was kept 1.2. UCS was performed with RHA to RM weight ratio 0.4 and 4 molar sodium hydroxide solution after curing of 14, 21, 28, 35, 42, and 49 days. In test samples B, 3 weight ratios 0.3, 0.4, 0.5 and 0.6 of RHA and RM was taken at constant sodium hydroxide solution. In test sample C, 3 concentrations 2 molar, 4 molar, and 6 molar of sodium hydroxide taken at the curing of 60 days, but other parameters were constant. Mojumder and Lasker, 2015, studied the unconfined compressive strength, UCS, test of geopolymer stabilized clay soil by an artificial neural network, N. For the geopolymerization, source materials were fly ash, FA, ground granulated blast furnace slag, GGBS, and blend of GGBS and fly ash. Amount of source materials were varied as 4% to 50% for GGBS, 4% to 20% for FA GGBS blends and fly ash. The molar concentration of alkali solution, M, used were 4 molar, 8 molar, 10 molar, 12 molar, and 14.5 molar. Ratios of alkali solution to binder were varied from 0.45 to 0.85 for geopolymer synthesis. Samples were compacted at a consistency of plastic limit with a tempting rod to remove air voids. 3 experimental program. 3.1 material used. 3.1.1 soil, The soil used in present work is taken from Shukta Farm Sitargunj, Udham Singh Nagar, Uttarakhand. Before collecting it, the topmost layer of the soil was removed by the spade up to 0.5 m depth. The soil was air-dried and pulverized for laboratory test purpose. Fig 3.1 shows the pulverized soil sample. 3.1.2 Fly ash. In the present study, fly ash was collected from Century Pulp and Paper Mill situated at Lalkayan, Nainital, Uttarakhand. The fly ash used in the study was Class F fly ash. 3.1.3 Alkali activator solution. For alkali activator solution 6 molar sodium hydroxide solution and 1 molar sodium silicate solution is used. 3.2 Laboratory experimentation. Native soil sample were prepared for determination of physical and geotechnical characteristics of the soil. The soil was mixed with 3 different percentages of fly ash, Fa, as 15%, 25%, and 35% by dry weight of soil sample. Soil was mixed with geopolymer binder, fly ash and alkali solution, and treated soil samples were prepared. Fly ash treated soil samples were mixed with for alkali activator solution 6 molar sodium hydroxide solution and 1 molar sodium silicate solution, L1. Table 1 presents the various geotechnical properties of the soil. For result and discussion, unconfined compressive strength, UCS, test is defined as the load per unit area at which a cylindrical specimen of soil will fail in the axial compression test. The UCS tests were conducted on soil added with different percentage of fly ash and alkali solution. The samples were tested for UCS on Helco hydraulic testing machine at strain rate of 1.25% mm/min after 0, 7, 14, and 28 days of curing. The stress strain behavior recorded during the UCS test. For soil and geopolymer mix, UCS values were presented in Table 2. 5 Conclusions. The study shows that the addition of geopolymer binder, fly ash, Fa, and alkali solution containing sodium hydroxide and sodium silicate improves the engineering properties of soil. The unconfined compressive strength of the treated soil samples found to vary with the concentration of activator solution in fly ash-based geopolymer. On increase in fly ash content, sodium hydroxide concentration and alkali solution percentage in the geopolymeric system improves the UCS, but when they are excessive of the optimal value, UCS decreases due to the precipitation at a very early stage before the polycondensation process in geopolymer.